for the other bits. I don't know what we're doing. I can't remember what we're doing. So first I want to come back to last week's stuff. I want to say one thing I don't know and one thing I do know. Yeah. So I think Amy asked, or someone asked, why, rather than going, well, this row in the simplex tableau means there's this equation is satisfied by all x1, x2, all s1, s2. And from this, we think it's an inequality like this, and then by our usual tricks where we round down all the coefficients, so x1 goes down to 1, I'll break it down. 1/7 goes down to 0, and 2/7 goes down to 0, and 20/7 goes down to 2. We have an inequality, which is what we've been doing. So the question was, why don't we go for the greater than or equal to inequality, and I still don't know. So if you do this, it does work. And that's the other thing that I wanted to show was it's kind of incomplete. So you get an inequality like this, and it has the slack variables in it, and you want to know what that means for the x1 and x2, in fact, right? Because, like, yeah, that's an inequality, and you can add it to your simplex tableau and all that. And you can keep pivoting. But if you want to know what that means for x1 and x2, what you do is, and that's probably something that the assignment would also like you to do, is where you have this formulation, okay, with slack variables. These equations tell you what S1, S2, and S3 is. So the first equation tells you when I put x1 and x2 on the right hand side, I get that s1 is 14, 7x1 plus 2x2 from there. And from the second one, I get that s2 is 3 minus x2. Okay, it's just from these equations. And then when I have an inequality like this, I substitute S for s1 and s2 from these equations, and I get that there's an inequality. Well, actually, the inequality we had from there, what it's doing is that it's 6x1 minus x2 is less than or equal to 14, which is the valid inequality. And so I still don't know why you shouldn't take this one. Well, you can do it if you want. It's just not the one that the algorithm takes. So it might slightly, not very much, but a little bit more work to add it into the tableau than the other one. But other than that, I can't see any reason why you shouldn't use this one. So I don't know. But in any case, it does give you a value of inequality as well. And that was this. Now, the second thing I want to say is that from this tableau that we have, okay, we decided to take the x1 row to derive a valid inequality, but we can take any row with a fractional value in it. What we can't do is take one that has a whole number that has an integer in the value. Because if you take one with an integer, you would get an inequality, but it wouldn't cut off this solution. So what you want from your inequality is that this would not be satisfied by it, because you want to get rid of this point and you want to solve on and on. Okay, that was the idea. Okay. So if I did take the S3 row, I would get that minus 2 over 7 S1 plus 10 over 7 S2 plus S3 is, well, I'll go for the less than or equal to 23 over 7. And now if I'm rounding down all coefficients, I have to realize that if I'm rounding down minus 2 over 7, well, that's something between minus 1 and 0. So rounding down gives me a minus 1. So this is going to be minus S1 plus S2, because 10 over 7 is something between 1 and 2, plus S3 and 23 over 7, that's just over 3, so less than or equal to 3. So that gives me another valid inequality from there. Does everybody still know what's going on? So then again, from these equations, I can substitute for S1 and S2 and S3. So S1, I get 14 minus 7x1 plus 2x2 from the first equation, and for S2, I get 3 minus x2, and for S3, I get 3 minus 2x1 plus 2x2, and that is less than or equal to 3. So what am I supposed to get here? I don't know. I'll go less. Oh. So this is then, what you get from this is 5x1 minus x2 is less than or equal to 11. So that would be another valid inequality that you can generate. And all these you can generate and keep adding and keep optimizing your linear programming until everything is integer. That should work. It might take a lot of time though. So this is not as good as the one that we got before. If this is no more than 2, then this is no more than 10, and this is negative, so it can't be like more than 11. So the first one we got was better. Okay. Any questions about valid inequalities? We'll do something else now. Has everybody got one? Good. Okay, this is a problem from Philip's lecture last year. Network models. Do you remember? Yeah? So to remind you, there was an example where, well, whatever the story is, we had a similar one with finding boys for girls and otherwise, but this one is a bit more real life, where you want to assign jobs to students. So you have 6 students and 6 companies, and every student has interest in some of them, which are listed here, but that's not really so important. And also every company has a list of students who would go there. So why is this here? So the picture is like this. It gives you a bipartite graph. Focus. So what do you have? We were doing this sort of thing. What you have is 6 students on the left, 6 companies on the right, and if they're compatible, you put an X. What you're trying to find is a matching. And the matching is a subset of the edges, so you pick an edge. So you pick some of the edges that are in there, and you want no more than one going from each company and no more than one going from each student. Then what you have. Okay, so for example, when you pick 1, 2, 3, these 4 edges, that satisfy the condition because every student only has one company. Some of them don't have anything, but that's okay. It's matching. And every company only appears once or not at all, which is also okay. Okay. So that's called a matching. How does one? Okay, what's the actual problem here? Or the question. So the question is, we are trying to find a matching which is like the largest possible. So we're trying to match as many students and as many companies as possible. Is that an easy question or a hard one? You could probably do it by hand on small examples. But there are several methods that you can use. So the method that you learned with Philip was that you can add some S&T and solve the maximum flow problem. Does anybody still remember that? Yeah? Okay. But there is a different method in which, I don't know what I want to do. In which what you want to do is use an integer programming model. And that's very similar to the problem we had with matching boys and girls, except there everybody could be matched to everybody and there was a value on how good that match is, whereas here you can only match some to some, and some of them you cannot do. So, I mean, it's pretty much the same. You can actually do the boys and girls problem, then you could just think of having all the edges there, then the ones that are actually not there, you would give them an objective value of 0, the goodness of match of 0, whereas the ones that you do have there, you would give them a 1, and then you can solve it using the previous formulation. But let's write a formulation, one that can't speak. That just fits this. So we'll have a UV decision variable for each edge from U to V. Okay, and then what we want is that this should be equal to 1 if student U is matched to company V, and it's equal to 0 otherwise. So this is exactly what you would probably expect by now. Okay, 0, 1 variables, which edges we pick into the matching and which edges we don't pick into the matching. And the objective is we just want to pick as many edges as possible. Okay? So we want to maximize the number of edges chosen. And the number of edges chosen is, how do we find it as a formula, as a linear function of the decision variables? Any ideas? You get a 1 for every edge you choose, and you get a 0 for every edge you don't choose. So how do you find the number of edges you've chosen? You add them all together? Is that what you said?
Sum.
Yeah, it's the sum of everything. You add them all together, all the XUVs for all the edges UV. So you add all the decision variables, and that's it. And what are the constraints? Yeah.
Things like the sum of the students going to one company is equal to 1 on them.
Yeah, that's true. So for every company, which we call V, you want that the sum of all the XUVs over all the students, well, where this exists, it's a bit floppy, but never mind, is no more than 1. And also for every student, you want, when you're adding all the companies that could be matched to, you want that they're matched to no more than 1. And that's everything. We really just want no more than 1 student, no more than 1 company. But the last thing we should state as a constraint is that the variables are actually binary as we intend them to be. So now, because I want to be annoying, I want to write these constraints as a matrix times vector. That's in a vector. So I want just like we did in linear programming when we were doing the theory of the simplex method and all that. So what would the matrix A be in this case? So X is just the X, A, Go, and all these decision variables up to XF Tesco. So it's a vector, a column vector of plenty of decision variables. But what is the matrix A? So in the matrix A, every row will correspond to one of the constraints. So we have like two parts of the matrix A, right? In the top part, those are the, let's say, the company constraints. And the bottom part, that's the student constraints. Just like we did above. And the columns, they correspond to all the decision variables. So if this one is the XA Go, and the second one is X, let's say B O, and the third one is X C Go, and so on. And we have decision variables for all the edges. Okay. Now what happens is the first constraint, when I look at the first company, it tells me that XA Go times 1. That's what it is. I'm just looking at, some of them will be there. B. What's the first constraint for the first company? I just look at all the decision variables that have a student and that fixed company, they roll, and I put them with coefficient 1, and all the others don't appear in the constraint, so they have a coefficient of 0. So what the matrix does is, wherever there's a Go in the decision variable, you get a 1, and where there's no Go, you get a 0, and like this, you get your first row. And the second constraint is for the second company, so it has some 1s and 0s, and the next one has some 1s and some 0s, and so on. And I like this, I get a constraint for each of the companies. Does that make sense? No. And then for the students, you do the same. So wherever there's a student A appearing, you put a 1. Okay, wherever there's a student B appearing, you put a 1. Wherever there's student C appearing, you put a 1. And so on. And they're all less than or equal to 0, less than or equal to 1. So the right-hand side B is just going to be all 1s. But that's not so important. What's important really is matrix A. Okay, and this matrix A has a special property which is here. So there is a class of matrices in maths that are called totally unimodular matrices. And the definition is of a totally unimodular matrix that whenever you pick a square submatrix, so you select a few rows and the same number of columns, and wherever they kind of intersect, you pick those numbers, and you do the determinant, and if the determinant is always +1, -1, or 0, then the matrix is called a totally unimodular matrix. So, what does that mean? Well, it's kind of not clear. So firstly, when you, okay, so do you understand what a square submatrix is? No? I just said it, but okay, let's say A is I don't know if it's totally unimodular or not. What a square submatrix is, I can take a number, give me a number between 1 and 4. 2. Thank you. So I choose any 2 rows, okay, let's say this one and this one, and any 2 columns, let's say the first 2 columns. And where they intersect, that's this and that and this and that. So I get a submatrix which is 1, 0, 0, 1. And its determinant is 1. So that's good. But if I wanted to test it using the definition, I would have to go for any for every square submatrix. So for example, there are square submatrices that are just 1 by 1. Okay, so every entry has to be 1, 0, or -1. But yeah, that's true. You only have 1, 0s, and -1s as entries in this matrix. So every 1 by 1 square submatrix actually has determinant 1, 0, or -1. That's good. Now for the 2 by 2, I have no idea. But maybe there is. Only. So the only bad 2 by 2 submatrix which doesn't have determinant of 1, 0, or -1 if all entries are like that, you would have determinant something like this that gives you determinant 2. And then you can put the -1 all corners can have, well, so you can put the -1 anywhere you want, and then you have one that has 3 -1 and the 1, and you can put the 1 anywhere you want. So these are the bad 2 by 2 submatrices. I'm not sure whether they appear in this or not. Maybe not. And then you would have to go for all 3 by 3 submatrices as well, and then the whole matrix has to have a determinant of 0, 1, and -1. So that's how you would test it if you wanted to test it using the definition. So that seems quite hard, but there is a sufficient condition. So if all these conditions hold, then the matrix is totally unimodular. Not every totally unimodular satisfies these conditions, but the matrix does, then it is totally unimodular. So like my matrix doesn't, because here it says each column has at most 2 non-zero entries, whereas my third column has 3 non-zero entries. So I couldn't use this criterion to decide that the matrix is totally unimodular. So the first condition is clear. We've talked about this. You can only have zeros, ones, and minus ones. Second condition is that you can't have more than 2 non-zeros in any column. And the third condition is that you can split the rows into 2 different things, 2 different parts, such that when you look at any column and you add everything in one part and you add everything in the other part, you get the same number in every column. Not like in it. Sorry, I didn't say that right. So in different columns, the results can be different, but in each column, the part 1 sum has to be equal to part 2 sum. Okay, so that we can use in this case, can't we? Is it only zeros, ones, and minus ones? Is it, how many non-zero entries are there in every column? So there's a 1 where either the student, so when you have a constraint corresponding to student A, you get a 1, and for all the other student constraints, you get a 0. And in the top part, for every student, so for every, the only constraint where you get a 1 is the one that corresponds to the first company. And here also is just to the first company, and then to the second company, and so on. So you get exactly 1, 1 in the top part, and exactly 1, 1 in the bottom part, which means there are exactly 2 non-zero entries. And the third condition, so when you look at every column, when you sum these, you get a 1. When you sum these, you get a 1. There's exactly 1, 1. So this matrix does satisfy the conditions, so it's totally unimodular. So now everybody is rightly upset because they have no idea why they should care about a matrix being totally unimodular. And the reason for it is that you have a linear programming problem where the constrained matrix is totally unimodular, and the right-hand sides are all integers, then no matter what the objective is, you will always get an optimal solution which is all integer. What does that mean for our problem? Is that a good thing or a bad thing? formulation again. Oh. So if you wanted to solve this, say using branch and bound, what would you do? Well, first you solve this linear program without integrality constraints. What's going to happen? Well, by the theorem, the solution will be all integer. No matter what the objective is, you could play around with the objective, you could put things like good matches and stuff like that. And so on. But you would always, just the first linear program would already have an all integer solution, so you don't have to do any branching, you don't have to add any inequalities, solve the linear programming relaxation, and you already get the optimal solution. So these problems are nice, but because they can be solved easily in the first relaxation. Okay, that's the kind of theory behind it. So totally unimodular, and therefore the LP relaxation of what's called the student company assignment problem has an all integer solution. Have I been cheating? A little bit. Because one thing I didn't put into the matrix is these binary constraints. Okay, so these binary constraints, what they would mean is that each of these has to be less than or equal to 1. And if I added them, then I don't know whether I would have a totally modular matrix or not. But I don't really need less than or equal to 1, because if I just say XUV is integer, it's the same thing. Because every one of these decision variables appears somewhere in a constraint. So it can't be more than 1, because when you add other non-negative numbers to it, you could never be 2, you could never get 1. So these are actually not needed. Instead of saying that they're all binary, you could say that they're all integer, and you'll get exactly the same principle. So I've not been cheating really. How much time is left? Not much. There's not enough time left for anything. Well, in that case, I can finish by saying that you have a homework problem, which is about totally unimodular matrices. And I think it's probably enough for the theory bit, so we can go back to trying some more ILP formulations for some problems from next week.